Okay, so here's another cell notation that's given to you and you're told to draw a cell. Draw a voltaic cell or a galvanic cell based on this right here. Well, okay, so again, the general form is that you're going to have the anode on the left and the cathode on the right. And what the heck is that? Did you forget it? Camguy, did you forget that that was a Cu or something? You just put a C there. It's a C. It's carbon. I'm going to tell you why. Because in the half reaction here that you would get when you have the permanganate ion and H positive together to form the oxidizing agent. And why did I know that that was the oxidizing agent? Hey, because this is going to be the cathode, and the cathode that's undergoing reduction. Reduction occurs at the cathode, and reduction is oxidizing agent. Now look, what did I tell you to do? Take this whole list anyway, this list of chemicals right here, and find on a table, a redox table, find the SOA and the SRA. And when you do that, these two together here, coupled together, form that SOA. That's the strongest oxidizing agent, way up here in the top left corner. And this guy right here, the zinc, is the strong reducing agent. So if that's the case, that being the strong reducing agent, take that equation in the data booklet or on your sheet and reverse it. Whoosh, like that, right? And then take that permanganate reaction and write it out exactly the way it says in the data booklet. And there's the voltage of it, 1.51 volts right there. Now notice that it's pretty easy to understand it. Here, the solid here is the zinc, so we're going to make the anode the zinc metal. Yeah, that's right. But what are we going to do here? When you look at this half reaction, you got this is aqueous, this is aqueous, this is aqueous, this is liquid water. Where's the solid? If you don't have a solid, here's the deal. Use an electrode that's an inert electrode. An inert electrode means inert, by the way, I-N-E-R-T, an inert electrode. An inert electrode is going to be something that will conduct electricity down it but won't react with the solution that you put it in. Carbon is an excellent, and by the way, carbon's black, so I don't know why I kept that red. Here we go, there's a black piece of carbon in that solution. And that right there will conduct electricity but won't react in the solution. You know what's another good inert electrode? Platinum metal. So, carbon or platinum. Now, what we've got then is these two half reactions, and when you take those voltages and add the reverse of this one, which is what used to be negative 0.76, reversed it, so I made it positive 0.76, add it to the voltage here, I get 2.27 volts, which is what you should get on the voltmeter, and if it doesn't read that, there's resistance in the wires, you know, and maybe you didn't scrape the zinc to remove all the oxide coating to be able to get good contacts with the little alligator clips on your wiring. All of those things provide resistance and might not give you the 2.27 volts in a lab setting that you should get theoretically. There's always a little bit of source of error there, right? But the thing is, to finish the diagram, who's going to migrate where? Because now, yeah, you've got the electrons going from the anode to the cathode, which is carbon, and the electrons go down the carbon, and they're going to feed what in the solution? Well, there's MnO4 negative swimming around in this solution. H positive means you put an acid in there. It's acidified. Well, which acid did you use? You just use an acid. Hydrochloric acid, sulfuric acid. Okay, let's just say hydrochloric acid. So, we've got H positive ions swimming around in that solution too, right? And it's going to form, when they go up there to gain those electrons, these guys here, we're going to get Mn2 positive coming off of here, and we're going to get water. Hey, by the way, permanganate is a real purple colored type of chemical. If you start to lose permanganate in the solution and gain this little pink one right here, the solution's going to actually change a little bit of a color. It's the same as that last cell that we did. If copper ions were being used up, a solution would become less blue because copper ions are being utilized. Just remember that, because there's color charts that you're given too for ions, and you might need to know what a solution is turning from and to because of the color changes of the ions, right? Now, in order to complete this is the cathode. Well, what's going to migrate? Migration, of course, occurs from one side to another. You don't migrate in the same beaker kind of thing. You go from one thing to another thing when you migrate. So, if this is the cathode, a cation has to migrate from here. Well, what's the cation? The Zn2 positive, which is in this solution right here, because this is going to be a zinc nitrate solution. And so, Zn2 positive. The cations migrate to the cathode. Now, who's the anion migrating to the anode? Well, permanganate can do it. Now, you're going to say, well, permanganate's got to stick around for the reaction. Yeah, but it's a stupid chemical. Some of them might actually go up, and they migrate. And they really do. You can actually see that migration taking place when you set up a cell like this. You can see that purple color move up there. And sure, some of it's moving just through simple diffusion, but some of it's being drawn to the other side too by this electrical movement that must take place with these ions. So here is an anion, that's MnO4 negative, that could migrate. But remember, that was maybe HCl, right? So maybe there's chloride ions that are in there too because of that acidified solution that could also migrate as well. So that would be how to set up a cell when you need to use something that like an inert electrode on the cathode side. Now, here's the thing too, by the way. Since this is gaining the electrons, the cathode, nothing on here is forming a solid, and nothing would be plated onto this cathode. It would just kind of, this manganese ion and water just kind of enters the solution. But in the previous example, when this was a piece of copper here, and copper ions were plating onto the copper electrode, that electrode was gaining mass. What's going to happen in this type of cell? Voltaic cell, spontaneous cell that's turning chemical potential energy into electrical energy, which has a positive E0 value. What's going to happen is that the cathode, generally speaking, when you've got a metal and a metal plating onto it, is going to gain mass. And what's the anode always going to do? The anode is going to lose mass.